Hi, this is Sanjeev from Bentley Systems. In this particular video, I'll show you how to use IS 1893-2016 in STAAD.Pro, and it talks about the implementation of this particular code in STAAD.Pro Connect Edition. So today's outline of this presentation is classified into introduction of IS 1893 Part 1 2016, what is new, discussion on equivalent static analysis, irregularity checks, discussion on parameters to be used for response spectrum analysis and the provision of torsion, and I will show you the recommendation of for the users. So we all know IS 1893 Part 1 is the mother code for earthquake analysis in India. It has got 5 codes, and the Part 1 deals with the general provisions and buildings. This code has been revised after 2002. This is the 6th revision, and major changes that we can see in this particular code is we are getting 2 different response spectrum curve, and this response spectrum curve corresponds to 5% damping, and for the buildings we have to use the 5% damping all throughout, whether it's a steel or concrete. So if we talk about the response spectrum curves, the top one is the response spectrum curve to be used for the static analysis, which is an equivalent static analysis, and the very next one is to be used for a response spectrum analysis. So if we try to understand what are the major changes, so the changes that are specified in this particular code is based on 2 categories. The category 1 is on the basis of demand, and category 2 is on the basis of capacity. So we are getting a new sets of approximate fundamental time period of the structure to be used in the static analysis, and new spectral acceleration coefficients value SA by G, and it corresponds to the 5% damping, and a method of analysis, and also we are getting new R factors. There has been a new provision for vertical acceleration coefficient AV. We are getting the minimum VB base shear from the static analysis, and we have to use the crack section analysis for the RCC structures. And if we talk about the capacity, and we have to check for the irregularities. Irregularities has been classified in 2 types: plan irregularity and the vertical irregularity. Plan irregularity consists of 5 parts, and vertical irregularity consists of 7 parts. We will discuss that later on in this particular video. We are getting different specifications to be used for the URMs, and we are getting a new specification for the shear walls allocation in the open ground story building. So talking about computation of TA, we are having 3 sets of categories depending on the lateral load resisting system of a building. In the first category, the building, we are considering the building with our moment resisting frame. In this particular category, we have got 3 subdivisions applicable for RC moment resisting frame, steel composite moment resisting frame, and the steel moment resisting frame. And there has been a new inclusion for TA, where we have to use the equation number 3. If we go sequentially, it's an equation number 4, where we are getting an equation by which we can find out the approximate natural time period with the buildings with the structural walls. And the last one is for the all other buildings. These particular equations can be used for the buildings with URMs in fields. And you can see there has been a change in this particular equations, and the proper locations of the square has been specified over here. This will be after the second bracket. And talking about the equivalent static analysis, we are here to discuss about the base dimension and the height. And if you can see in the 3 figures, the height of the structure and the base dimension is dependent on the formation of the building or its location. And here we require some input from the users, because this is something that the program cannot understand, and that's why we have introduced 3 parameters: HT parameter to be used for the height of the building, For the base dimension in x and z direction, we have dx and dz parameter. Now we have got the new sets of response reduction factor, and in the program we have implemented this as an automated option. If we click on in the seismic definition the generate option, you can see that there has been a drop down option by which you can choose these R factors. Now for the design vertical acceleration coefficient, which is AV, and now this particular code has some special recommendation, and if your you can see the highlighted portion talks about this particular stuff, and this has to be decided by the users whether you need to consider the vertical acceleration coefficient in your analysis. That means you need to perform analysis for earthquake load in the y direction. So the conditions are, as you can see, if the structure is located in zone 4 and zone 5, if you have any type of irregularities, if the structure is at a soft soil, and this is mandatory for the bridges, and if your structure has a long span. And the same thing if the structure has horizontal overhangs or an overhang in the members or the subsystem. So how we can do that one? The clause number 6.4.6 talks clearly on this, and for the buildings we can see that it will be 2/3 of the computed value, and the SA by G is specified as 2.5, which is the maximum, and this has to be used in the program. So the program that I will show you that in the program this this particular consideration is automatic, and now we are allowing you to consider equivalent static load in the y direction. The program will be generating the load on the structure. This is very important minimum base shear criteria, and in this particular version of the code we have a term called rho, and the minimum base shear will be computed as rho into W divided by 100. This is been done by the program automatically, and in the output we provide a check on that one. This particular section talks about the portion of the structure if that is, that is below the ground, and we are considering the structure in two parts: the portion which is above the ground and the portion which is below the ground. We are computing the seismic weight for this particular two portion, and for the upper portion there is no reduction in the base shear, and VB for the upper portion is being calculated and it is being distributed as an story shear. And for the lower portion, the AH value is being reduced by considering the fact if the structure is at ground level there will be no reduction. If it is if the base of the structure is at 30 meter below the ground level, there will be 50% of your VB computed, and any portion which is at intermediate location you will be getting interpolation factor, and that is being applied on AH for the portion which is below the ground, and then we are computing the horizontal base shear and it is distributed for the portion which is below the ground. And in order to tell the program which portion is below the ground, we have introduced a parameter called GL in the STAAD.Pro Connect edition, and this particular parameter has to be the coordinate of y coordinate rather for the ground level. If you input this particular parameter, the program will consider its effect. This is one of the important section, clause number 6.4.3.1, where the code talks about crack section analysis for the RCC members if it is subjected to the earthquake forces rather. So RC and the masonry structure, the I gross of the columns should be 70% of the actual one, and for the beams it will be 35%, and here there will be no reduction if the members are of steel. So let us try to look into the program. I have got a model ready with me, and in this particular model I have properties where I can see for the beams 400 millimeter by 300 millimeter. The depth of the beam is 400 millimeter, and for the column it's 400 by 400, and it's a sort of irregular shape. And this is a very simple model, and in this particular model, if I go to the loading, I will get to see that there are certain things that has been incorporated, and this implementation requires two things to be incorporated in your model. First thing, we ask our user to provide a mass reference load case. This is a mass reference load case, and in this particular mass reference load case, we provide the seismic loading that will be required to compute the seismic weight in the three orthogonal direction. And in order to understand that this is a mass reference load case, we generally take it as an unsigned forces, and apart from that one, we require to provide the rigid diaphragms. So the command is can be put from node specifications, and if you go to the node specification, you will find the option for the rigid flow diaphragm. So it has got 1 2 3 4 5 diaphragms levels. And here what I have done is, in this particular model, I have added a seismic definition. In the seismic definition, you can see that these particular definitions, you have the option for the generate. So if you generate it, you have the option to choose the city, R factor, the importance factor, and then type of soil and type of structure. Now the important thing is that we have incorporated all of this equation that I have shown in the previous slide, and they are written over here, so you can choose any one of them from here. And once you are done with that one, for the property reduction, I can go to the analysis and design, and for the property reduction, let us show you some different option. I can go to the beam from the specification, and you have got the option for the property reduction. So for the property reduction, you will get to see that there has been a new option available, which is code specific IS 1890-2016. And in order to consider this particular factor, I have to use two property reduction factors that you can see from here, where you have to provide reduction value as 0.7 for RIY and for RYZ, which is applicable for the columns, and for the beams we have 0.35 and 0.35, and that has to be applied to the beams. And once you have added this, you can assign it to the required members. So after the assignment, you can see this particular stuff. Now if I am okay with that one, I can go on and create seismic load case. And in the seismic load case, you can see that in seismic load case, I will come to the torsional portion later on. I have provided X directional seismic load case. Next, I have the Z directional seismic load case, as you can see, and for the Y direction, we are allowing the generation of seismic load case in the Y direction. You can get to see the loads generated as I have already analyzed this particular model. So I can open up the output file. In that output file, if I look into the results of X directional load cases, you can see that in X directional load case, I just forgot to mention that in seismic definition, I have used a GL parameter. So on using a GL parameter, I have used the structure type 4. That means the building with URMs. This is the last equation, and I mean in the code. And here the damping is 0.05 because the response spectrum that I have to use should correspond to the 5% damping, and the program will use it internally. And this is the ST5 parameter, and the importance parameter that I have provided is 1.2. So if I look into STAAD output, we can see that it has divided the entire thing for the above the ground level portion and below the ground level portion, and it has calculated the time period in x direction, and VB mean has been computed just as you can see over here, and VB actual, since the VB actual is greater than the VB mean, so it will be used in the computation of lateral story shear. And the same thing has been considered for the portion of the structure which is below the ground. So it is also reporting what will be the base shear if the structure is at the ground level and if the base of the structure is below 30 meter the ground level. Here I have used a command perform analysis print load data. So for that one, and we are getting a summary and seismic weight, age value, VB calculated, mini VB mean, and what is the VB final that has been considered. So if I scroll down to get the results, I will get that one. Later on I will show it to you. And another interesting thing is that the generation of y directional seismic force. Here you don't require to compute the time period, as the SA by G is 2.5, which is a constant. So straight away I can once again open up the output file. In that output file, this is for irregularity checks. I'm going to, this is in y directions basically, and here you can see there is no requirement of computation of time period, so it has skipped. SA by G is constant, and the same logic has been applied for the generation of seismic load above and below the ground in the y direction. And here you require to consider the property reduction factor, so that I have already explained to you. Now let us go on discussing the other part of this particular presentation, and you can see from here, this is the property reduction stuff that I have discussed. The next is the irregularity. For the irregularity, I can I have to put some attention to this particular portion, and for the irregularity checks there are some important irregularity checks for the plan and the vertical direction. For the plan direction, the irregularities that I need to consider is torsional irregularity. Here I can consider the floor as a diaphragm and provide the apply the lateral load onto the diaphragm and find out the minimum and maximum displacement. If the maximum displacement is more than 1.5 times of the minimum displacement, I can have an idea that it is torsionally weak. And apart from that, I need to consider the natural period corresponding to the fundamental torsional mode of oscillation is more than those of the first two translational mode. This is an particular check which we can perform by, if we are going for a dynamic analysis, say we want to extract the mode shapes and the frequencies by using the modal calculation requested command, or if we perform a response spectrum analysis, by default it will go for the modal extraction and we will get to see the mode shapes. And this particular computation also requires the cross-sectional properties reduction. And if we see, what we expect is that the pure translational mode should come first, then the torsional mode. So that has to be checked, and in STAAD.Pro we have incorporated this particular check as an automated option. We have got the option for the reentrant corners. So the criteria has been provided over here. If A by L is more than 0.15, then we can consider that there has been a reentrant corners, and if you have any such irregularities, the 3D dynamic analysis is required. For the excessive cutout, The pictures are quite self-explanatory. So generally, if you have opening, if the opening is more than 50% of that um, total floor area, we can consider that diaphragm not to be a rigid diaphragm rather than flexible, and this particular condition has been provided for the opening which is situated at the edge. The next option is out of plane offset in the vertical elements. If you have got a condition like this, we call it as an irregularity. And for the non-parallel load resisting system, in the first figure we can see that the frames, which are the moment resisting frame, which are not connected at 90 degrees. So that is an indication that we have got irregularities, and this is with shear walls. So the vertical irregularity, the most important thing is the stiffness irregularity, where we have to use the soft story, and here the soft story definition has changed. So if the stiffness of the story is less than the story above, that will be called as a soft story. Mass irregularity, if a seismic mass of a particular floor is more than 150 times the floor above, that will be, and it will be declared as a mass irregular condition. Vertical or geometric irregularity, horizontal dimension of lateral force resisting element in any story is 125 than the story below. Discontinuity in the vertical load resisting element. Strength irregularity, this can be computed after we perform the final design. And floating of the staff column, this is absolutely unacceptable. And irregular modes of vibration, here we have to check if the first three modes contributes less than 65% of mass participation in each principal plan direction. In terms of STAAD, it will be X and Z, and the modes are separated by 10%. So instead, we have some of the irregularities incorporated as automated option, and in this context we have got torsional irregularity, re-entrant corners, mass irregularity, and irregular modes of vibration as an automated option in STAAD.Pro. So I will be opening the STAAD.Pro output. Before going into that one, if I have got a model where I have got rigid diaphragm commands, and rigid diaphragm commands requires a mass reference load case, if these two things are there into the model, you can go to the analysis and design, you can go to the miscellaneous command, and you can go to the float diaphragm option and check on these two options, check soft story and check irregularities. On doing this, if I go to the input file, I will get to see that two commands will be added. The float diaphragm is there. Now after the float diaphragm, I can see a command that has been added, check irregularities, code IS 1890-2016. And after the rigid diaphragm, you can see a command called check soft story, IS 1890-2016. And after adding this from the UI or from the input editor, you can analyze your model, and you will get to see some of these outputs from the STAAD. So the first output after the float diaphragm, you can see, is soft story checking, and the programs compute the stiffness of a story, and then it reports you whether it's a soft story or not. And if we talk about irregularities, the first irregularity is based on the displacement type. And for the torsional irregularity, we have to check two stuff. First thing is the displacement based approach that we have discussed. So from the displacement based approach, which is if we have got a diaphragm, what is the minimum and the maximum deflection in the direction of the application of the load, that has been computed in X and Z direction, and as a result you can see the status. And I would like to mention that for modal extractions result, where you will be getting the time period of a torsional mode and the translational mode, and you have to check if the time period of the torsional mode is higher than the time period of the translational mode, that particular check has to be done manually at this particular point of time. I mean, that has not been implemented. For the geometric irregularity checks, you can see the projected length, and as the floor plan suggests, it has become re-entrant. There are some re-entrant corners. So for the mass irregularity checks, you will be getting the report for that one. And one thing we can at this particular time understand, that we are providing a mass reference load case. By doing that one, we are defining the masses at each floor level, each diaphragm level ladder, which is definitely a floor level, and the program can compute the mass irregularity check. And for irregular modes of oscillations, we require a dynamic analysis to be performed. So we can look into that. Now let's move on to the other part, and let's come to the response spectrum analysis. In the response spectrum analysis, as you can see from this particular option, that the response spectrum curve is being plotted. That was a long demand, and one of the interesting thing that you can see, the response spectrum data that the program is considering. Here the PGA value for this particular response spectrum curve was 1, and the program is multiplying the SA by G with G, and that's why you are getting this particular accelerations value, which is the SA value. And there is no requirement, if we are using the code specified response spectrum, the curve will be plotted over here, depending on the subsoil class, and you can see the scale factor is considered as 1. And the modal response is the response spectrum analysis is a particular analysis where we analyze each and every mode, and the modal results are to be combined using the modal combination method. And as per IS 1893, we can use CQC. For closely space mode, we have got CSM, or we can use the SRSS. And for torsional provision, we have got the two equations to consider the torsional eccentricity. And here we have got the EDI, which has two part, ESI and percentage of the building plan dimensions. So ESI is the difference between center of mass and center of rigidity. If you have got the rigid diaphragm, the program can compute the center of rigidity and center of mass, and their difference will be considered into the analysis. And 1.5 and 0.05, and also in the second case 1 and 0.05 are to be used separately using the different load cases, which will be discussed in the model. There has been another requirement, which is whenever we are performing a response spectrum analysis, the base shear computed from the response spectrum analysis has to be compared with the equivalent static analysis. And for two orthogonal direction, we can compare the base shear separately, VB by VB in X and VB by VB in Z. And for the Y direction, the maximum of these values computed in X and Z direction need to be used. The program can do it internally, and let us look into this particular model. In this particular model, what we have done, we have applied a response spectrum load case in X with positive torsion computation. Here we have used two parameters, DEC and ECC, and in DEC the parameter is 1.5, and ECC, which is an accidental eccentricity, the value is 0.05. And in another case, for torsion in opposite direction, the value will be 1 and minus 0.05. So, and here the torsional provisions need to be used in X and Z direction. There is no requirement in Y direction. So in the Y direction, no torsional, I have not used any torsional value, any parameters which is required for the torsion. And if we look into the STAAD output file, we'll get to see some of these informations, just like if I go to the participation factors, and here this is in x direction, and VB by VB dash has been considered as 4.7. Even I have to check. So, and if I scroll down, go to the participation factor, that is in z direction, that has been computed by the program. And if I come at the last, here you can see the maximum of the two above VB by VB dash is being considered in the y direction. And one thing that I need to add is that if I want to consider the y direction, I should at least consider 90% of the mass participation. Now come to the irregular modes of vibration, and since I have performed the response spectrum analysis, and we can see the the summation of mass participation in two orthogonal plan direction, which is x and z, is more than 65%. And you can see the modes are not separated by 10%. So in this particular video, I tried to explain you what are the things and what are the automation we have done for IS 1893 implementation. And at the end, I'll thank all of you for your time. If you use this particular version of STAAD.Pro, which is the latest version of STAAD.Pro, you will be able to use IS 1893 specification totally. Thank you.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.